Welcome to the video lecture for section 4.1, Basic Concepts of Probability. My name is Jorge Gavillan, and this is for STA 2023, Intro to Statistics. So in this section, we're going to be talking about probability values. And so probably the most important thing is that probability values are only values between 0 and 1. So an event that has a small probability, such as 0.001, corresponds to an event that most likely will not occur, or it's a really rare event. We're also going to talk about odds and how they relate to probabilities, but we're not going to talk about payoffs. And so I got rid of those last few slides that went along with the textbook slides. So basics of probability: an event is any collection of results or outcomes of a procedure. A simple event is an outcome of an event that cannot be further broken down into simpler components. Sample space for a procedure consists of all the possible simple events, and that is that the sample space consists of all outcomes that cannot be broken down any further. And just like anything else, when probability is best explained using examples. So here's a table. We're going to use lowercase b to denote a baby boy and lowercase g to denote a baby girl. And so the first one is a single birth. So having one girl is a simple event, right? You can't break that down any further. Now, in a single birth, the sample space is either a boy or a girl, because those are two possibilities. And so when you talk about sample space, you really have to include all of the possibilities that can occur when this trial occurs, if you will. Now, if you have three births, an example would be two boys and a girl, which will be boy, boy, girl, or boy, girl, boy, or girl, boy, boy. And right now, the sequence of those letters might not mean anything, but I'll show you a tree diagram in class. And so if a couple has three children, the possibilities are the sample space here given. So they can have all three can be boys. That's one extreme. All three can be girls. That's the other extreme. And then you have in between possibilities. So two boys and two girls. And there's several ways that you can denote two boys. You have boy, boy, girl, or boy, girl, boy, or girl, boy, boy. You can also have two girls, which can be boy, girl, girl, or girl, boy, girl, or girl, girl, boy. And so some people would say, well, that's the same thing, right? If I get boy, boy, girl, and boy, girl, boy. Not always. Sometimes the sequence of events is important, and it makes two events different. So simple events. With one birth, the result of one girl is a simple event. The result of one boy is another simple event. They're individual simple events because they cannot be broken down any further. Now, with three births, the result of two girls followed by a boy is a simple event. Just like when you roll a single die, the outcome of getting a 5 is a simple event, but the outcome of an even number is not a simple event. So, not a simple event. With three births, the event of two girls and a boy is not a simple event because it can occur with three different simple events, right? Girl, girl, boy, girl, boy, girl, boy, girl, girl. And so, again, sample space is all of the possibilities. So some notation for probability. Capital P denotes a probability. A, B, and C denote specific events, and those capital letters can be anything. They don't have to be A, B, and C. We just use capital letters. So P of A denotes the probability of event A occurring. And so the possible values of probabilities is between 0 and 1. So if an event has a probability of 0, that means it's impossible, it's not going to occur. If it has a probability of 1, that means it's certain it will occur. It also have a 50-50 chance, and anything in between. So the following three approaches for finding probabilities results in a value between 0 and 1. And I just, when we denote it here, is 0 less than or equal to the probability of an event A less than or equal to 1. So the probability of an event A has to lie somewhere between 0 and 1 inclusive. So one way that we can do it is what the textbook calls it the relative frequency approximation. This is also known as the empirical probability. And this is where you can conduct or observe a procedure and then count the number of times an event A occurs. So the probability of A is then approximated by P of A is equal to the number of A occurs divided by the number of times the procedure was repeated. The next one is the classical approach to probability, and this requires equally likely outcomes. So if a procedure has n different simple events that are equally likely, and if event A can occur in s different ways, then the probability of A is equal to the number of ways A can occur divided by the number of different simple events. Now, be careful when using classical approach. You have to be certain that the outcomes are equally likely. So let me give you an example. If I flip a coin, getting heads or tails, that's a 50-50. If I roll a die, getting a 1, 2, 3, 4, 5, or a 6, those are all equally likely. It's 1 out of 6 that I get one of those values. Subjective probabilities, the P of A, the probability of event A, is simply an estimation using knowledge of the relevant circumstances. Honestly, subjective probability, this is full of bias, right? So I can give you an example. I'm a Yankee fan, so I can say the probability the Yankees are going to win the World Series is 92%. Well, who knows, right? I'm being subjective because I'm a fan, and so always be careful when you're dealing with subjective probabilities. So another way that we can find probabilities is by doing simulations. So sometimes none of the preceding three approaches can be used. So a simulation of the procedure is a process that behaves in the same ways as the procedure itself, so that similar results are produced. And probabilities can sometimes be found using a simulation. And so let's say we wanted to flip a coin 1,000 times. We don't literally have to flip a coin 1,000 times. We can actually use software to simulate that process. So how do we round probabilities? When expressing the value of a probability, either give the exact fraction or 3 decimal places. And so either way, whichever way you're comfortable with. So when a probability is not a simple fraction, such as 2/3 or 5/9, you can express it as a decimal so that the number can be better understood. Sometimes decimals are a little better because a lot of times, and you'll see this in class, if something has a probability of 0.44, I'll say it's a 44% chance that it'll occur. So sometimes I'll convert those into percents. The law of large numbers. So as the procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. So to give you an example, I know that if I flip a coin, I have 50-50. That's the actual probability. That is the classical probability. That does not mean if I flip a coin 10 times that I will get 5 tails and 5 heads. If I flip it 20 times, get 10 and 10. No. If I flip it 10 times, I might get two tails and 8 heads, right? And so I can get any variation. I might get 5 and 5, but chances are that I won't. However, the law of large numbers states that if I repeat the process, so if I'm flipping it 10 times and that's one trial, if I repeat that process again and again and again, like if I do it 1,000 times, what's going to happen is that the probability of tails and heads will approach 50-50, and that's what it means by the law of large numbers. So you have to be careful. The law of large numbers applies to behavior over a large number of trials, so 1,000 trials, or 10,000 trials. So it does not apply to one individual outcome or a trial. If we know nothing about the likelihood of different possible outcomes, then you should not make the assumption that they're equally likely. So the actual probability depends on factors such as the amount of preparation or the difficulty of the test. So you have to be careful. Something like flipping a coin or rolling a die or something like that, those are pretty standard. And so, you can go ahead and use a law of large numbers with something like that. So here's an example using relative frequency. Find the probability of dying when making a skydiving jump. So in a recent year, there were about 3 million skydiving jumps. 21 of them resulted in deaths. So we're going to use the relative frequency approach. So the probability of skydiving death is equal to the number of skydiving deaths divided by the total number of skydiving jumps, which is 21 over 3 million. And you can see that that's a very small value. So the classical approach cannot be used because the two outcomes, dying or surviving, are not equally likely. A subjective probability can be estimated in the absence of historical data. So here's another example. In a study of U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving during the same period. And so based on these results, if a high school driver is randomly selected, find the probability that he or she texted while driving during the previous 30 days. And so instead of trying to determine an answer directly from the given statement, first we can summarize the information in a format that allows us to understand. So 3,785 texted while driving, 4,720 did not text, for a total of 8,505. So now we can use relative frequency to find the probability of texting while driving, which would be the total number of drivers who texted while driving divided by the total number of drivers in the sample, and that gives us a 0.445. So there is a 0.445 or a 44.5% probability that if a high school driver is randomly selected, he or she texted while driving during the previous 30 days. We're going to talk about complementary events. The complement of event A, denoted by A hat, consists of all outcomes in which event A does not occur. And so, again, let's go back to the example here. We know that 3 million jumps were made, 21 people died. So 21 divided by 3 million is the probability of dying while doing a skydiving jump. We're going to find the probability of not dying when making a skydiving jump. And so that's simply going to be the difference between the probability of dying and 1. And so if I were to do 1 minus the probability of dying while skydiving, I would get the 0.99993. And so those are complements. There are two possibilities in this example. Either I die or I don't die. And so if I add the probability of both of those events, I need to get 1. If I don't get 1, then something's missing. And that's how we're able to find the complement of events. So the next thing is significant results. So rare event rule for inferential statistics. If under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or greater than what we typically expect, and with that assumption, we conclude that the assumption is probably not correct. When we get into hypothesis testing, this will make a little bit more sense. So the author in the textbook talks about significantly high number of successes. So X successes among N trials is significantly high number of successes if the probability of X or more is unlikely with a probability of 0.05 or less. That is, X is significantly high number of successes if the probability of X or more is less than or equal to 0.05. Now, this is not a rigid number. This is just a number that's used a lot in statistics. And then the flip of that is the probability X or fewer, it would be significantly low. So let's review real quick. Probability of an event is a fraction or decimal between 0 and 1 inclusive. The probability of an impossible event is 0. The probability of an event that is certain to occur is 1. The P of A is the probability of event A. P of A hat is the probability that the event will not occur. That is the complement of the probability of A. And then we're going to talk about odds. So actual odds against event A occurring are, it's the ratio of the probability of the complement divided by the probability of the event, usually expressed in the form of A to B, where A and B are integers. So we reduce using the largest common factor. If A is 16 and B is 4, then we express it as odds of 4 to 1 instead of 16 to 4. So the actual odds in favor of event A occurring, the ratio of P of A over the probability of the complement of A, which is simply the reciprocal of the actual odds against the event. So if the odds against the event are A to B, then the odds in favor would be B to A. And that's the end of 4.1. Thank you.